the mole. Finally in chapter 3, we begin to learn about a fundamental relationship in chemistry, the mole. If we take a look at our periodic table, hydrogen has an average atomic mass of 1.008. And we know that we are given permission to report our average atomic masses to the 100th place. If we're not talking about atoms, we know that the unit will be grams. And let's just choose oxygen. And that's 16 grams. Well, how about, let's say, molybdenum? Well, that reads 96.96 grams. Well, what do these masses represent? If we attach gram, is that the mass of one atom of hydrogen? The mass of one atom of oxygen? A single paperclip feels like a gram in your hand. And a paperclip has hundreds and hundreds and hundreds and hundreds of different atoms. So there's no way these masses represent a single atom. What they represent are a mole of that element. All right, so what is a mole? A mole, ladies and gentlemen, is a counting unit. We are familiar with a dozen. A dozen means 12. And you can have a dozen of anything. A dozen Sharpie markers, then you have 12 Sharpie markers. A dozen cups, then you have 12 cups. We could have a dozen fingers, and then we have 12 fingers. So we can have a dozen of anything. Well, you can have a mole of anything. A mole of Sharpie markers, a mole of plastic cups. And a mole is worth, just like a dozen is worth or represents 12, a mole represents 6.022 times 10 to the 23rd of whatever you have. So if you have 1 mole of Sharpie markers, it would be this number of Sharpie markers. Now, that number, it is a grand underestimation to call this a large number. This is crazy big, crazy. So, just to bring to life, I have some kind of thought experiments, but can I just tell you first that we give this number a name. It's called Avogadro's number. Now, Amadeo Avogadro actually did nothing toward creating this number or measuring and calculating this number, but we credit him and honor him by naming this after him. So this is Avogadro's number. Okay, if we have 1 mole of hydrogen atoms, then it's this many grams of hydrogen. Or if I have this many grams of hydrogen, it's 1 mole, which means I have Avogadro's number of atoms of hydrogen. Okay, so again, how can we try to understand this number? Well, in your note packet, I've given us some of these kind of thought experiments. So if we had a mole of donut holes, it would cover the entire Earth 5 miles deep. Wow. If we had a mole of basketballs, it would be about the size of the Earth. So this number is beyond our comprehension. However, if you would take your 2 hands and grab a hold of a little pile of sugar that would fit in your hand, you would have Avogadro's number of molecules of sugar, not individual crystals, but molecules. So why this crazy big number. Well, we need a crazy big number of atoms to be able to have measured masses that we can work with in lab and with our hands and with our instrumentation. So, all of these atomic masses represent 1 mole of each element. Now, 1 mole always means this number. So if I have 1 mole of oxygen, it's that number. If I have 1 mole of molybdenum, it's that number of molybdenum atoms. But they differ in their masses. That should make sense. Just like if I had a dozen Sharpies, well, that would be a very different mass than a dozen elephants. So the number is the same in a mole, but that doesn't mean the same mass. Well, I don't know about you, but I definitely see conversion factors. If we say 1 mole of molybdenum is this mass of molybdenum, and that 1 mole of molybdenum would be Avogadro's number of atoms of molybdenum, well then, we see conversion factors. Okay, what do we mean? Well, let's see. My favorite number is 3. So let's just say we have 3.33 moles of chlorine. And what if I want to know the mass that would be? All right, well, we've learned dimensional analysis. It's up to you if you want to put your given over 1. All right. Can we relate moles of an element to the mass of the element? Absolutely. The average atomic mass, there are 35.45 grams of chlorine in every 1 mole of chlorine. Mole and gram are related through the average atomic mass number reported to the 100th place. So we would just do our math and so 3.33 times 35.45, and we'd be reduced to 3 sig figs. We're assuming that's definitely a measurement. So this would be 118 grams of chlorine. We need to identify which element we're speaking of. Okay, well, how about instead of moles, what if we were given mass? So what if we had 0.148 grams of, let's just say, gallium? And I want to know how many moles that is. Can we relate grams of an element to moles of that element? Absolutely, through the average atomic mass reported to the 100th place. So gallium is 69.72. I need to check. Yep, 69.72. Now, remember, what we read as the average atomic mass, that's gram in 1 mole. And we're restricted to 3 sig figs again. And so, 2 mole of gallium. That would be our answer. All right. Well, let's go back to the 3.33 moles of chlorine. Now, I'm given an element. The smallest piece of an element is an atom. So if I have a mole of element, I can find out how many atoms that would be. Now, how do we relate mole and atom? Avogadro's number. Avogadro's number. So, if I have 3.33 moles of chlorine, all right, I want to cancel moles and I want to go to atoms. Okay, if I'm in mole of element, the smallest piece of an element is an atom. So, 1 mole of chlorine would be Avogadro's number of atoms of chlorine. And just being sure that I am entering this correctly on my calculator, and 3 sig figs, 2.01 times 10 to the 24th atoms of chlorine. And if I would be given atoms, so let's say 500 atoms of, let's say, calcium. What if I want to know moles? Well, can I go from atoms to mole? Well, I'm dealing with an element. Atoms are the smallest piece of an element. So yes, 1 mole of calcium, Avogadro's number of atoms. And now, moles and grams, they were measured. But atoms, that's a counted number. That's exact. Avogadro's number comes from experimentation. So this has the opportunity to limit us to 4 sig figs. This would be exact. We don't measure atoms, we count them. So we're limited to 4 sig figs here. And that would be 8.303 times 10 to the negative 22nd moles of calcium. It makes sense because we know how many atoms we need to make a mole, so 500 is a minute fraction of a mole. All right, one more. What if I did measure a mass amount of an element on a balance, and let's say the balance reads 30.932 grams of, let's say, iron. And I'd like to know how many atoms that is. How many atoms? All right, well, So, grams. Well, we've been pulling grams from the periodic table, and we know that the average atomic mass of iron is the amount of grams in 1 mole. And this is an element. Smallest piece of an element is an atom. So I can use Avogadro's number. So not all of our problems, just like in chapter 2, will be done in one conversion factor. So here, if I'm starting with mass, I'll of course put grams of iron to moles of iron. So we're traveling through the mole. And we have 56.85 grams in 1 mole. And then we know if we have 1 mole of element, that will be Avogadro's number of atoms of that element. And so, being very careful, this has 5 sig figs. Oh, this has 4 and this has 4. So we're actually limited to 4. Let me just get the answer here. And to 4 sig figs, 3.277 times 10 to the 23rd atoms of iron. Okay, so we are going to practice many more together. This is our first taste of what a mole is.